Hey everyone, welcome back to Calculus 2. In this will be lecture 26 of the course, and in this section we're going to begin discussing alternating series. So far, we've really confined ourselves mostly to series whose terms have all been positive. So where we'll be going in this section is towards looking at series whose terms can be both positive and negative. And we'll start with the simplest such series, and that series is called alternating series. So let's jump into it. All right, we'll call this section 4.5, alternating series. And let's start with just an example of what do we mean by an alternating series. So here's an example. The sum from n equals 0 up to infinity of negative 1/2 to the nth power. Okay, so another way to write this is n equals 0 up to infinity of negative 1 to the nth power times 1 over 2 to the n. And so, as you can probably see, or if not, you can easily see when I point it out, this series is called alternating because of this piece here, this negative 1 to the nth power factor, right? So this piece here is going to be what causes the series to alternate. This is what causes the series to alternate between positive and negative values. Right, so every other term is going to, be positive, and every other term is going to be negative. Right, so the first couple of terms here would be like, so when n is equal to 0, negative 1 to 0 is just 1, so this would be 1, and then minus 1/2, plus 1/4, minus 1/8, plus 1/16, and so on, right? So you can see how they alternate. This technically is a geometric series that's alternating. So this is an alternating geometric series. Okay, so all that really means is that r in this case is equal to negative 1/2. Okay, the common ratio is equal to negative 1/2. This happens to be an example where the even terms occur, the positive terms occur on the even indices, right? So the positive terms occur on even indices, right? So n equals 0, 2, 4, 6, and so on. Now in this example, the negative terms therefore occur on the odd indices. Right, so whenever n is equal to 1, 3, 5, 7, and so on. Right, and that's just because the exponent on the negative 1 piece here is just n. Right, now it can occur the other way as well, just as easily, right? If the exponent is n plus 1 or n minus 1, then you'll have the reverse, right? But an alternating series is always going to be one or the other, right? You'll always have positive terms on the even indices or positive terms on all of the odd indices. There's never going to be any variation in that theme, right? That's why it's called alternating, because it literally flips back and forth from positive to negative. Okay, let's talk about when an alternating series converges. Let's get a nice test out here. Okay, so for this theorem, let's let a of n be a positive value. Then the alternating series. Now there's two options here, n equals 1 to infinity of negative 1 to the nth power times a to the n. And the other one would be, just the case where the odd ones occur on odd terms, on even terms, would be n equals 1 to infinity of negative 1 to the n plus 1 times a to the n. Right, so the only difference between these two is that here you're going to have odd on odd, so you're going to have, negative on odd, and here you're going to have negative on even, right? There's really no like practical distinction between these two. It's just you got to be careful. The proof requires us to kind of call this out a little bit, but fundamentally speaking, there's no major distinction in how you treat them, right? So letting an be a positive value, it means this piece of it's positive, right? And the negativeness, when a term is negative, it comes wholly from this part here, the negative 1 to the nth power. Now, if you think about it, you can always kind of do this with a series. If a series term is negative, it is always possible to kind of pull the negative 1 out of everything. So that's that. And what's the theorem say then? Well, if a of n is greater than 0, then the alternating series, these two, converge if the following two conditions are met. All right, so the first condition is that the limit as n goes to infinity of a of n is equal to 0. So, namely, the nth term of the series must converge to 0, right, in the limit. Must go to 0 as the limit as n goes to infinity. And second, a of n plus 1 needs to be less than or equal to a of n, and this is going to be for all n. Okay. Now, when I say for all n, what I really mean here is for all but a finite number of, for all but a finite number of terms. Right? Namely, it's okay if the first 4 terms don't satisfy this condition, so long as every term after the 4th term does. Or it's okay if the first 50 terms are kind of don't satisfy this condition, so long as all the 51 and on all do meet this condition. So that's what we mean for all but a finite number of terms. More concisely, we sort of say for all n, but really keep in mind that this is a little bit flexible. Okay. So the theorem basically says, look, if you got an alternating series, you can write it like this. That series, whichever way it is going to converge if, the nth term has a limit of 0 as n goes to infinity, and if the series of terms, the sequence of terms, is decreasing, right? So namely, as you go further out, the terms get smaller, right? Okay, so let's go ahead and prove this. We can prove this theorem. It isn't too difficult. It requires a little bit of algebra and some reasoning, but it is not beyond the scope of calculus 2. So let's take a look at it. Let's consider the alternating series, and we'll just write it like this: sum negative 1 to, and we'll go with the n plus 1 version times a to the n. Okay, so for this series, the partial sum, and this is going to be, where 2n is even, is, you can write it like this. So if we have s of 2n, okay, s of 2n, this is going to be equal to a1 minus a2 plus a1 minus a3, or sorry, a3 plus a4, sorry, plus and a5 minus a6 plus dot 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 plus a of 2n minus 1 minus a of 2n, right? And so on, right? It just continues, infinite series. So all we've done here with the parentheses is just group them, right? So this would just be a1 minus a2 plus a3 minus a4 plus a5, right? But grouping them is going to help us see, some structure that we can exploit for this proof. Now, because, right, one of the assumptions of the theorem is that a of n plus 1 is less than or equal to a of n, right? So that's one of the assumptions of the theorem. Because this is true, each of the terms in this sequence is non-negative. Okay, now what do we mean by that? Well, I mean, if it isn't clear, this is a positive value, right? Because a2 is smaller than a1, right? So when you do when you subtract the two, you get a positive value, right? And the same thing for all of the remaining terms, right? So this is greater than 0, this is greater than 0, and so on, right? And this is greater than 0. Okay. Oh, sorry. This is not an infinite sum. This is a partial sum. So stop there. Okay. Right. So this is all of these terms are non-negative, and so therefore, you can say that the sequence of partial sums is going to be a non-decreasing sequence. Okay. All right. So we've got a non-decreasing sequence of partial sums here. Now notice we can also write, right, taking this thing here and kind of bringing it down, we can also write this in a different way. We can write it like this. S of 2n is equal to a1 minus a2 minus a3 minus a4 minus a5 minus dot 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 minus a of 2n minus 2 minus a of 2n minus 1 minus a of 2n. Right, so take a moment and look at this and make sure you can see exactly how this is done, right? So the a1 is positive, so it's just sitting there. Now, a2 is technically minus a2, right? So we just factor the minus out and you get a positive a2. Now a3 is positive, so we factor out a negative and it becomes minus a3, and we do this, so on and so forth, right? All the way down the line. Okay, and so what does this mean? Well, what can we infer from this? Well, what this implies then is that S of 2n is going to be less than or equal to the value of a1. Okay, now why is that true? Well, again, this is greater than 0, right? Same thing here, right? Because a3 is smaller than a2, so when I subtract it, I'm going to get a positive value. Same here, same there. Those are all positive quantities, and I'm subtracting positive quantities from a1, right? So S2n is naturally going to be less than this thing, right? Because it's equal to this thing minus all this other stuff. Okay. Okay, so basically the partial sum S of 2n is less than or equal to the first term of the series, and this is going to be true for all n. So this is true for every integer n, right? So not just, large integers, but also small integers as well. And so what does that mean? Well, that's going to imply that the sequence of partial sums is bounded. Okay, it's bounded. And it's bounded because, it's certainly bounded by this value here. right? Whatever that happens to be. Okay, all of the partial sums are going to be less than a1. All right, so it's an upper bound on it. It's also a non-decreasing sequence. So this sequence, S of 2n, is monotonic and bounded. Right, now technically we say it's monotonic increase and bounded above. Right. Okay, so it's monotonic and bounded, and that's going to imply that the sequence is going to converge. So therefore, the sequence converges to some L. Okay, some value L, finite value L. Okay. And so what we have then is, because S of 2n minus 1 minus A of 2n is equal to S of 2n, and because A of 2n goes to 0, we have, right, this is by assumption, we have that the limit as n goes to infinity of S of 2n minus 1 is going to be equal to the limit as n goes to infinity of, obviously, S of 2n plus, right, now bringing this over the other side, plus the limit as n goes to infinity of A of 2n, which we know is equal to L, right, that's this piece, L, and this is going to 0, and there we have it. Okay, and so we can see then, you know, that S of 2n and S of 2n minus 1 both converge to L, and so it follows that the series will converge to L. Okay. Okay. So that's the proof. Right? It just uses the fact that, I mean, those assumptions are pretty strong. Right? Those initial assumptions are strong assumptions. Right? We say that you know, these two things have to be true in order for the series to converge. So namely, the nth term has to go to 0, and it's, you know, the terms have to be decreasing, right, for all but a finite number of terms. Okay, so if you have those two things, then you have a convergent alternating series. Okay, very good. So let's take a look at some examples. This is kind of how these sections go, right? You start with you know, some definitions, then you bang out a test or two, and maybe prove it if you can, and then you do some examples. Okay, so here's the question. Does the series n equals 1 to infinity of negative 1 to the n plus 1 power times 1 over n converge? Does this converge? Well, so notice, right, here you've got, I mean, this is a p-series, right? So notice that this is, you know, you've got your a of n equals 1 over n, and your a of n plus 1 is equal to, obviously, 1 over n plus 1. And, you know, clearly, 1 over n plus 1 is less than or equal to 1 over n for all n, right? That's true. Right, so that means, you know, that the series is decreasing. Also note, of course, this is a p-series, so note that the limit as n goes to infinity of 1 over n is equal to 0. Right, so you've got the two conditions met. You've got, you know, the fact that it's decreasing. You've also got the nth term going to 0. So, you know, therefore, the series must also converge. Okay, it's going to head to some limit, some finite value. Okay. Excellent. Excellent. Here's another series let's talk about. So the series is n equals 1 to infinity of n over, now this one is negative 2 to the n minus 1 power. Right, the question is, does this converge? Does this guy converge? Well, let's rewrite it first of all. So we have n equals 1 to infinity of n over negative 2 n minus 1 power. Let's rewrite it in a form that's a little bit nicer to look at. So let's take the let's see, how do I do it? We'll just write it like this. So we've got the n over the top, and then we'll just pull the negative 1 out down below. That'll be fine. So n minus 1 and then 2 n minus 1. All right. Okay, so to apply the alternating series test, what we need to check the conditions, basically, don't we? So we need to note a few things. So we can establish that the nth term and the n plus 1 term are going to be decreasing, right? The terms are going to be decreasing in the following way. We can start with just the fact that you have 1/2 is going to be less than or equal to n over n plus 1, right, for all n. Okay. And what we can do then is write it like this. Right, it's going to imply that 2 to the n minus 1 over 2 to the n is going to be less than or equal to n over n plus 1 for all n, right? So all we're doing is exponentiating appropriately. Okay, we can do a little algebra on this, and we can see clearly that n plus 1 times 2 to the n minus 1 is going to be less than or equal to n times 2 to the n. Okay, and then from this it quickly follows that n plus 1 over 2 to the n will be less than or equal to n over 2 to the n minus 1, right? And so your a n plus 1 term here is this guy, n plus 1 over 2 to the n, and we see that that's less than or equal to n over 2 to the n minus 1, which is your a of n term. Okay, right, so that's kind of a tricky way to establish this. Usually you would work this in reverse. You'd start by assuming this is true and then back it, and then sort of reduce it down to something that is true like this, and then it's a reversible argument. But I kind of did it ahead of time, and I can you can see that it goes this way. Okay, all right. So what does this establish? Well, so this shows that the terms are all decreasing. Okay, they're all decreasing. So next, the question is, what about the limit of the nth term? Right, and so next we need to look at the limit as n goes to infinity, of basically n over 2 to the n minus 1. Now, this is not, so when you think about this limit, you can see that this is going to produce direct substitution will produce infinity over infinity, an indeterminate form. So direct subs will produce infinity over infinity, which is an indeterminate form. And so what we have to do is, well, one of the ways to deal with this is to employ L'Hopital's rule. Okay, so we want to use L'Hopital's rule here. Right, and so instead we would consider the limit as x goes to infinity. Now we're kind of switching variables because we're thinking of this more as a function, and so we think, because we want to take a derivative here. So think of this limit again, infinity over infinity. Well, tentatively this limit will be equal to the limit of the ratio of the derivatives. So let's see what that looks like, if that limit exists, of course. So the derivative of x is 1. Now what's the derivative of this? Well, you may recall it's natural log of 2 times 2 to the x minus 1 power. And so now we have a form that is not an indeterminate form, right? So this limit will be 0, right? Because this piece of the denominator is going to grow without bound, and so this is going to be equal to 0. Okay, so what this all implies, if you recall the L'Hopital's rule section, what this all implies is that the limit as n goes to infinity of n over 2 to the n minus 1 is 0. Okay, and so the fact that a of n plus 1 is less than or equal to a of n, and that the limit as n goes to infinity of a to the n is 0, these two together imply that the series converges. And so let's write it all out here. This will be -2, and then it's n minus 1. And so this implies that the series converges to some finite sum, some finite value. This is a nice way to write that, shorthand way to write that. Okay, very good. And so that is another example. Let's do one more example. Examples are the king here, right? At this level in mathematics, not only not only does it help you understand the thing you're learning, but calculus is really the time to shed any algebra problems. And so doing lots and lots of examples, seeing lots of different functions is really the way you learn here. So let's consider the convergence of this series. -1 to the n plus 1 power, and then it's going to be n plus 1 over n. Right? Does this converge? Okay, so a nice little series here. Now let's think about, first of all, let's talk about this condition here, see if it holds here. So a of n is equal to n plus 1 over n, and a of n plus 1 then would be n plus 2 over n plus 1. Okay. So it turns out that, this does meet the criteria, right? N plus 2 over n plus 1. This is going to be always less than or equal to n plus 1 over n, which is your a of n, right? Right. You can just try a few values, and you'll see that actually it's definitely true, and that condition holds. So check. So that's good. What about the limit? What about the limit of the nth term? All right, so next let's consider the limit as n goes to infinity of, n plus 1 over n. Well, unfortunately, this one does not it does not, the limit does exist, right? We know that the limit's 1, right? This is polynomial over polynomial, first degree, so it's a ratio of the leading coefficients, and that would be 1. So the limit, definitely exists and is finite, but it's not equal to 0, right? Recall that the alternating series test demands that the limit of the nth term as n goes to infinity be equal to 0, right? So this series would fail on the first condition of the alternating series test. Okay, so we cannot say that this series converges. Now, be careful, right? This doesn't mean that it necessarily diverges. It just means that we don't know that it converges. Right? So the theorem says the alternating series converge if the following two conditions are met. Right? The limit needs to be equal to 0, and the terms need to be decreasing. Right? So we can't say that the series converges. Okay, I guess that doesn't necessarily imply that the series does diverge. Okay. Excellent. Excellent. Let's take a look at the next section here. So, with alternating series, you may have noted the way that we leveraged partial sums during the proof of the alternating series test. And so this brings up an interesting technique of identifying the alternating series remainder. Okay, and this is something that can be useful in practice, but also we'll use it later on when we get into Taylor series. So alternating series remainders. Okay, so for a convergent alternating series, the partial sum S of n can be a useful approximation for the sum of the entire series, for the sum S. So S of n can provide a useful approximation of S, right? S being the sum of the infinite series, S of n being the sum of the first n terms of the series. So the next theorem will tell us something about how close S of n is to S. Okay, how close S of n is to S. Okay, and this is a nice one. So if a convergent alternating series satisfies the condition, all right, let's go ahead and write this all out. So if a convergent alternating series satisfies the condition that a of n plus 1 be less than or equal to a of n, then the absolute value of the remainder, we'll call it R of big N. Okay, the absolute value of the remainder, R of big N, so the absolute value of the remainder R of n involved in approximating S by some S of n. So this remainder is going to be less than or equal to the first neglected term. Now, what do we mean by that? Well, let's write it out here. So S is my true my true sum, the sum of the entirety of the series. This is a convergent series by assumption, right? And if I want to approximate it using a partial sum, S of big N, then the remainder, which is basically this quantity, take the convergence value minus the sum of the first big N terms, and we're going to call that R of n, the remainder. This value of this thing is going to be less than or equal to a of n plus 1, where a of n plus 1 is just the next term in the sequence, right? So if S of n is the first big N terms, and this is the next one, the first one to be left out. Okay, it's the first neglected term. Okay. All right. Excellent. So we can prove this theorem as well. This is has a nice proof. So the series. So the first thing to think about here is that the series obtained the series that you obtain by deleting the first n terms of the given series should satisfy the conditions of the alternating series test and have a sum of R of n, right? So let's talk about that for a second. So the series obtained by deleting the first n terms of the given series satisfies the conditions of the alternating series test. Okay, and it's going to have a sum of Rn. Right, so is that clear? Right, so if I've got the sum, right, so I've got my A1 plus A2 plus A3 plus dot 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 plus A of big N plus A of big N minus 1, or big N plus 1 plus A of big N plus 2 plus dot dot dot, right? So the series obtained by deleting the first n terms, right? So that's going to be basically everything over here, right? So this is the series obtained by deleting the first n terms. So when I delete these terms, I'm left with this. Now, these terms are going to satisfy all of the conditions of the alternating series test, right? Namely, the limit of the nth term is going to be 0, and also the terms will be decreasing. Okay. So satisfies the condition that a of I is greater than or equal to a of I plus 1, and that the limit as I goes to infinity of ai is 0, right? So those are the two conditions. Okay, so that's true. And then we just call this Rven. Right, so this is just Rven. Okay, so let's talk about this piece. Right, this is what we would mean by the remainder. Right, this piece here, the first n terms plus this part is the total series, right? Right, so this is the partial sum, this is the remainder. So let's talk about the remainder, Rven. Well, it's equal to s minus s of n. Right, we know that. It's equal to, we can talk about it as, basically break these things down. So this would be n equals 1 to infinity of negative 1 to the n plus 1 times a of n. And then minus the sum where n is equal to 1 up to n of negative 1 n plus 1 a to the n. Sorry, I should have probably done this in a separate page. That's okay. Right, so this is just s. This is the nth partial sum of s. Okay, no problem. Let's write it out. Right. So basically what we're going to do is we're going to say, okay, we just want the terms that come after n. Right, so let's write what those are. So negative 1 to the nth power, okay, and then times a of sub n plus 1, okay, and then plus negative 1 to the n plus 1 power times a of n plus 2 plus, and then we'll just go one more, negative 1 to the n plus 2 power times a of n plus 3, and then so on, right? It just keeps going. Okay. And so we can factor the negative 1 out of this, right? If we factor n negative 1s out, then we should be able to figure out what all of the values here are, right? So, keep in mind what happens to negative 1 as you continuously exponentiate it. It just kind of toggles back and forth, right? So I can take out negative 1 to the nth power, and if I pull that out of here, I'm just left with a to the n plus 1. Now this one, what am I left with? Well, I would be left with negative 1 to the first power, which is a negative, right? So that would be minus a to the n plus 2. And then over here, I'd be left with negative 1 to the second power, and so that would be plus a to the n plus 3, and so on, right? Minus, and then dot, 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 right? The whole thing. So this is an infinite series here. Okay, I'm going to flip pages. I'll rewrite that. So I've got negative 1 to the nth power, and then I've got a sub n plus 1 minus a sub n plus 2 plus a sub n plus 3 minus dot, dot, dot. Okay, so that's where we left. That's what we left off with. And so we can do the same trick that we previously did with this, namely kind of rewrite these terms so that it's one big difference, right? So the way we would write this is, well, actually first, let's take the absolute value, okay? So what happens when we take the absolute value of this? Well, basically the negatives all drop out, right? Right, so this becomes a to the n plus 1 minus a to the n plus 2. Basically, this piece up front disappears. Plus a to the n plus 3 minus dot, 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 right? So the whole thing. That's the absolute value. Okay. And with this, we can do our little rearrangement trick. So let's write this as a sub n plus 1 minus a sub n plus 2 minus a sub n plus 3, right? And you'll see here that we're just basically successively factoring out negatives, right? So that we can write it in this form. Right, and so on. Okay. Right, and so we know here, just like before, we know that this is greater than 0. We know that's greater than 0, right? And so, consequently, this whole thing is going to be less than or equal to a of n plus 1, right? A of n plus 1 is, this guy here, and we're just successively, subtracting off positive values, and so naturally this entire thing will be smaller than this guy. And so that's the theorem, isn't it? Right? That's where we are. So let's finish it up. S minus S of n, right? The remainder, we called that the remainder, denoted at R of n. The remainder is this whole sum. And we can see here clearly that this is going to be less than or equal to a of n plus 1. So basically the first neglected term. Okay, perfect. All right, so we've got that. That's great. It's a nice little proof, kind of simple, allows you to prove some pretty interesting things using just kind of some simple maneuvers. Okay, let's use this to approximate a remainder. So let's do an example, basically. Let's approximate the sum of n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n factorial. Let's approximate this by its first 6 terms. Okay. All right, so first of all, before we try to approximate this, we have to make sure that the series converges. Right, so let's make sure this converges. So a of n plus 1 would be equal to 1 over n plus 1 factorial, which is less than or equal to 1 over n factorial, which is a of n. Right, so check, we've got that. And what about the limit of the nth term? Well, clearly the limit as n goes to infinity of 1 over n factorial is indeed 0. Right, so we definitely are going to converge here. Okay, so the series converges. Let's approximate it. Well, the sum of the first 6 terms, that's S6, right? Right, S6, so we can write them out pretty easily. This is going to be equal to 1 minus a half plus a sixth minus 1 over 24 plus 1 over 120 minus 1 over 720. Okay, that's 1, 2, 3, 4, 5, 6 terms. Right now, if we do the math, I've done the math ahead of time on this. I didn't think we'd want to do this by hand. You get something like 0.63194. So you get this pretty nice number here. So then we can say that S minus S6, that's the remainder. We need the remainder. Anytime you're approximating something, you need the remainder, right? So S minus S6 would be the remainder here if we estimate S using that 6th partial sum. That's going to be less than or equal to A7. All right, so what's the 7th term of this series? Well, it's 1 over 7 factorial, which is 1 over 5040, which is approximately 0.0002. Okay, so what we can say then, S is between, right, S6 minus A7 and S6 plus A7, right? So it's kind of in that interval. It's going to be in that interval. And so practically speaking, this is going to be 0.63194 minus 0.002, and 0.63194 plus 0.0002. Right, so it's going to be in there, and technically those numbers are 0.63174 and 0.63214, right? So it's pretty tight range actually for this guy. It's a pretty tight range. It's, you'd probably be safe to say it's approximately 0.632. So right in the middle of those two numbers, probably. So there's a good example. All right. Let's take another example. Take a look at another example. Sometimes a series, so we've been talking about alternating series, but sometimes a series may have both positive and negative terms, but not be an alternating series, right? Not actually be an alternating series. An example would be the series n equals 1 to infinity of sine of n over n squared. Okay, so so this is just right, sine of 1 over 1 plus sine of 2 over 2 plus dot dot dot, right? And so we know that some of these terms will be positive, some of these terms, this should be over 4. Some of these terms will be negative. It's going to have both positive and negative terms, but it's not an alternating series. It's positive and negative because the sine function will vary. Okay, and it's not strictly speaking an alternating series. Okay, so let's consider to figure out whether this converges or not. Let's consider the absolute value of the series. All right, let's consider this guy. We'll use kind of a direct comparison argument on this for this series, but we know that the absolute value of the sine of n is going to be less than or equal to 1. Pretty much for all n, right? Well, for all n. Okay, so what can we do? Well, let's compare this to something. Right, so if I have the absolute value of sine of n over n squared, a good comparison would be 1 over n squared. Right, and in this case, we can see that the less than or equal is going to work. Right, this is going to be true for all n, right? Right, at most, the numerator will be 1. Right, and many times it'll be less than 1, which is going to make this piece smaller. Okay, so by the direct comparison test, then, right, this is just direct comparison. We know that this guy here converges, and so this other one must as well. Right, we know that that's going to converge because, and we can write it out, because the sum of 1 over n squared is less than infinity. Right, we know this one. This is an easy one to see, and we can establish a term by term comparison here, and so that means this is going to converge as well. So again, this isn't the original series though, right? This is not the original series. This series is all positive. This series has got some negative values in there, right? So there's a theorem, and this will be the next theorem we talk about. This next theorem is going to tell us that the original series must also converge. Okay, and so if the absolute value converges, then the original series must converge as well. So theorem: if the sum of the absolute value of a series converges, then the series itself converges also. Okay. Right, and so that is going to be true. Now, we won't prove that, but this is one that I think you could probably figure out on your own, right? Or you could crank out a book, and there'd probably be a proof in an appendix somewhere. Let's use this. Let's do an example. So the question here is, does the sum from n equals 1 to infinity of -1, and then this is just trouble right here, n times n plus 1 over 2, that's the exponent on -1, divided by 3 to the n, does this converge? Well, you know, this seems, I mean, if you take away this exponent, this is straightforward, right? But the fact that you've got this crazy exponent up here creates a lot of problems, right? So let's consider the absolute value of this. The absolute value series, right? So consider this one, n equals 1 to infinity of the absolute value of this. Right, now what is the absolute value of this? Well, it couldn't be easier, right? It's literally, this is all just 1 when you consider the absolute value of the terms. So it's literally n equals 1 to infinity of 1 over 3 to the nth power. Right, this is geometric series, common ratio of 1/3. This is going to converge, right? So the absolute value series converges. And that's going to imply that the original series converges as well. Okay, so this guy right here, yes, does converge. Okay, all right, very good. Okay, so that's where we'll end this one. And I mean, I know that was kind of a quick treatment, but you know, there's a lot more to be said about these kinds of things. Next time we'll get into ratio and root tests, and then we'll be ready for kind of the grand finale of Calc 2, which is the power series and Taylor polynomials. So we'll see you all then. Take care.